Hey, I missed the 15. Sorry. Sorry for keep doing that for no good reason. Okay. Hello, Aminata. Hello. All right, she gave a hello. All right. Hello, Victoria. Hello, you. Okay, I'm going straight to chat. Hello, good afternoon, Raina. Good afternoon, Melanie. Good afternoon, Victoria with the double. Hello, sorry, Anthony. Good afternoon, Caitlin. Good afternoon, Zoe. Hello, Aminata with the double. Good afternoon, Vicky with Where is Vicky? Oh my God, it's just not the same without her avatar. I'm just
I'm
sitting.
at work right now. The avatar is on my laptop.
Oh, right, it's Thursday. Right, of course. That's so nice. Well, she just got voice. We just got. That's a Vicky voice. That might have been. Wait, do I want to call attention to Okay, great to hear Vicky's voice. Might be the first time. Anyway, okay, right, and of course you're right. I got to thank you all again. Of course, it's third. Right, this is that whole silly thing where we're all on a different. So it's very nice of you all to be here to do in any way you can. That's awesome. So good afternoon, Vicky, and everybody. Okay, I totally get it. Right, of course. Okay. So we're gonna shift gears entirely. Well, we're gonna shift back to this whole like harmonic oscillation thing. Um, so yeah, I guess let's just do it. So the goal is to get to the goal is to get to the two equations that are on the board here. Um, and yes, good afternoon, Gabriel. Good to see you, and good afternoon, Kian. Good to see you with the avatar too. And good afternoon. Ooh, David. Is that? Do I recognize that? I'm just yeah. You have my and I'm and she's got the right. All right. Yeah. Okay, I really need to start. But good, Gabriel, and good Aminata. And hello, Joel. Yes. And now it's got my curiosity.
Good
No.
afternoon, Professor.
Good afternoon, Mohammed. Good to see you. And thank you. And good to hear you. I mean, and direct chat person. I think I know where you were. I think I get it. We should talk about the timing at some point, but no, I totally get it. Direct chat person. Um, and David, I'm just curious because I'm a little bit of a, I mean, do I know what that is, or is that just a thing? Like, that's not a thing. Is it a thing, the David? All right, anyway, whatever. I'm like, it's okay. Anyway, um, okay. What I just want to say, we're going to get into back into oscillations and waves now. Sort of this is like the sort of centerpiece of the course in a way that we're finally getting to. But two quick things. One, the thing I'm about to explain is definitely like an explaining thing. Like it's not on a homework sheet. It's just an explaining thing, but it's big and it often is on an exam. Like, so you're going to want to take notes on the thing I'm about to do. You're going to want to try to get your mind around it. It is what it is. But I'll also just say, therefore, number one, every semester this is like I explain this in a big way, and sometimes more than once, and sometimes not. But with the thing I'm about to explain to all of you and try to draw and all that, if it I would encourage you to look up past videos of mine of it because I never say it exactly the same way twice, and sometimes I say it better than others, and it's a big deal. So feel free, especially as we get closer to an exam or something, which I can't even think about right now. Feel free to be aware that this is on tons of other videos of mine, and it's called staggered oscillations. The key word is stagger, really. So you could look it up that way. And the other thing is that someone's in the waiting room. Well, that's the main thing. That's the main thing. So the two equations that are on the board right here are where I'm trying to go. I don't think we've done them yet. That they are the goal. Uh, one of them, the bottom one, was written on a board a couple days ago before I realized that we had to do something else first. And if you see it on just for whatever it's worth in your PDF, if you in the PDF of notes and stuff, if you see this equation on another pile of notes from another day. The truth is, in retrospect, I think I wrote it wrong. So cross it out. Like it had Z's in it, and it's okay if it had Z's in it, but I think it had one too many Z's in it. So just destroy and discard that. But anyway, here we go. Oh, no. Sorry. Okay, sorry. Sorry, one second. Direct chat thing. Okay. Um, so here we go. Consider, meaning, so that says consider. Consider this new arrangement that I have not said anything about, but that has not come up in homework. Just consider it. Imagine you're in a lab doing the file. But first, let everybody into the room. Okay. In fact, I'm also going to change the view on the screen. Something like this. And something. Okay. What I want you to consider, and please do draw this, and well, yeah, please do draw this. This is a sketch, obviously, um, but it's supposed to be a sketch of a bunch of harmonic oscillators, each of which has the same mass, has the same stiffness, right? So it's a bunch of harmonic oscillator. It's a bunch of harmonic oscillators. It's a bunch of harmonic oscillators that all have identical parameters, right? Identical material properties. Oh, good afternoon. Yes, good afternoon. A bunch, good to see you. A bunch of, I'll write it. Right. First thing I'm specifying, so I'm making an arrangement here, a thought experiment that could be a real experiment, where I'm taking a bunch of simple harmonic oscillators, right, SHOs, but no problem, direct. I mean, thank you, direct type person. Got it. Bunch of simple harmonic oscillators that all have the same material properties. Like you open them out of the box, they're all from the same type of box, same bat factory. You open up each one, right? And then that's like so each one is the same mass and the same stiffness. And therefore, because of the nature of simple harmonic oscillation, you know before you even do anything with them, each one will necessarily oscillate at the same rate, at the same angular frequency of radians per second, right? Like you automatically, and that's already an interesting property of oscillators, that the angular frequency or the rate of oscillation, the cycling rate, is fully determined by the material properties. Doesn't matter how you set it up. You just know in advance. Once you know the material properties, the parameters, you know the rate that they'll oscillate. So each one of these oscillators is what we would ultimately therefore call an identical oscillator. That okay, and then let's imagine that we hang them from the ceiling. We make them vertical, kind of like you did in lab 2, or we put them on springs that are on the lab table. Whatever, we set them all up so that they are free, each one of them, to oscillate, let's say, vertically, and then we space them out along an x-axis uniformly, right? Like note it. So assumption number 1 is that they are all identical oscillators. Assumption number 2, that they're equally spaced. In fact, I'm going to write this more clearly on the next. So we're setting them up so that each one of them is free to oscillate along an axis that from here on in, I'm going to call the y-axis, right? I mean, in the lab room, you can picture it as vertical. Although I want to say very quickly, I'm not, just like you found out in lab 1, I'm not suggesting that gravity will play any role in any of this, or that we need to worry about any role played in gravity. I'm just saying role played by gravity. I'm just saying set them up so that they're each free to oscillate along the same axis, which might as well be vertical, and which from here on in we're going to call y. Then distribute the oscillators. Sorry. The oscillators are distributed uniformly, i.e., equidistantly, along a perpendicular axis, which we'll call x. Okay. And then the final, you with me? So we're spreading out a bunch of vertical springs on a lab table, and we're putting the first spring over here, and then the second spring like a meter away or a centimeter away. Excuse me. We're putting like the 0th spring over here, and then the first spring a meter away or a centimeter away, and then the second spring like 2 centimeters away or 2 meters away, whatever, right? So in our mind, we could put a y-axis right through the very 0th spring, and we can put an x-axis in our mind, and each spring is free to oscillate around, or each mass is free to oscillate around the x-axis along which all of them have been uniformly distributed. Okay, you get that. Then the last assumption I'm going to make is stagger the phase constants uniformly as well. And that's the key to the whole thing. And you can see that in the picture. Well, sort of. You can see it in the picture. Like I'm saying, and now this is where the math is going to come in and everything. I'm saying you take a bunch of vertical springs, you spread them out horizontally at equidistant intervals along the horizontal axis. But then you set them in motion and you arrange it. And this is what's maybe a little hard to do with just primitive springs. Maybe it's easier to do with like, a computer program that drives the springs or something like that. But anyway, but what you do is you set them up so that each one of them is out of phase with the one before it by a constant amount. For some reason, I always have a hard time saying this, but that's because it's so simple that I overcomplicate it. Like exactly what you think I might be trying to say is what I'm saying. Okay. So basically, like if you start your stopwatch when the very zeroth spring is at amplitude position, then at that moment, which would be a fine thing to do, then assume that at that moment when the very first one is at when the very zeroth one is at amplitude position, then imagine that the very next one, the first one, is let's say a quarter of a cycle already into its phase, like it's already at equilibrium position, and set it up or assume so that the next one, the second oscillator, is already at 2/4 of a cycle into its phase, like it's at pi radians, it's already at the negative amplitude position. And the next one is 3/4 of a way into its cycle. It's exactly, in other words, what I'm literally asking you to picture, and I mean this, I'm asking you to picture the simplest possible way we could arrange a bunch of identical oscillators so that they're not all in phase with each other. If they're all like the literal simplest thing we could do with a bunch of oscillators would literally put them all next to each other and have them all literally in phase, right? The absolute simplest thing we could do would be to have a whole bunch of oscillators all together going up and down and up and down. That's literally the simplest thing we could do. But my argument is, or my statement to you is, that is so simple that it's too simple. It's stupid. It's not stupid, but it is stupid because once you have a whole bunch of oscillators going up and down, and there's nothing to learn or nothing to see or nothing to do that you couldn't have done with one just long bar that was going up and down and up and down, right? Like a whole bunch of oscillators that are in, and I think I've mentioned this once before, a whole bunch of oscillators that are literally in phase with each other really just are one big oscillator. So I'm asking you to go one step further than that. I'm asking you to imagine, what if we took a whole bunch of oscillators and staggered their phases just enough so that like something happened so that we can make use of the fact that there were multiple oscillators, but we staggered their phases in the simplest possible way we could, because we always like to do that in physics, like be as simple as we can and no simpler, right? So what's the simplest possible thing we could do is to stagger these things in phase by a constant amount, right? So as always, I'm over talking it, like you know what I mean. Whatever you're thinking that this picture is supposed to say in this, with no tricks up your sleeve, is what I'm trying to say. But now let's talk about the math of that. Well, I'll raise your electronic hand if you're with me, and I can go on. Like I can go on, right? Like you get what I'm like asking you to picture. Raise your electronic hand. There's a thank you, Zoe. Thank you, Victoria. Thank you, Aminata. Okay, that's 5 people. Good enough for me. All right, so let's talk about the math of what that would mean. Well, let's say, for example, that each oscillator is like a quarter cycle ahead of or behind its neighbor, right? Remember a quarter. Sorry, Anthony, is that a question? Or are you just raising your hand from before? I'm sorry. Is it? Oh, okay. Darn it. You can ask a question. You can ask a question. Okay, okay. Anthony has asked questions before, actually, or he certainly has said things before. So what's a quarter cycle? Remember, a quarter cycle is pi over 2 radians, right? Because a full cycle is 2 pi radians, right? So let's imagine that that's the case. In other words, that when the first one's like at amplitude, then when the zeroth one is at amplitude, the first one is like at equilibrium, and the second one is like negative amplitude, like that. So then that would mean in this example, then like I could write an equation for each one of the oscillators, right? The very zeroth oscillator, so to speak, the oscillator that's at the y-axis, that's why I'm calling it zero, right? Like that's on the edge of the meter stick that goes horizontally. That one could be expressed by an equation that would look like that if I started my stopwatch when it was at amplitude position. And then the first one would look like that, right? Stop me if you're not with me, but like this is the whole concept of phase constant, right? But then the next one would look like that, right? Which is to say, I'm just looking at the chat, right? You see where I'm going with it? Right? You see where I'm going with this? You're with me so far. Stop me if you're not with me. Oh, yes, that's a yes. Thank you. I thank you. I'm another. Right. Okay, so you're with me. Okay, so therefore what? So therefore, if we're also believe right, like yeah, it, if that's true, and we're also believing that each one of these, like I'm calling like the zeroth oscillator, the one that's on the y-axis, and the one oscillator, the first oscillator is the one that's like a meter away or a centimeter away, or if they're all equal distant, then that actually means that what the phase like the only thing that differed in each one of these equations was the phase constant. And by the way, everybody, I hope you realize each one of these phases that I wrote was like measured relative to the zeroth one, right? I mean, each one is out of phase by pi over 2 by its neighbor, but therefore, okay, you get my point, or if you don't, tell me, but therefore I'm saying, right? Like each one of those equations was an oscillator, but we could capture the whole thing in one swoop if we want and write something like this, right? I mean, I look at this carefully with me, everybody. Hopefully, I'm going step by step, so each step is like not a big leap. But I think when you put all the steps together, like we're going to have something here. So, so make sure you're with me. I'm saying like if you want to know if you want to know what the y position is of any given oscillator at any given time, we have one equation that will predict that, as long as you not only plug in the time that you're looking, but you also plug in how far you're looking on the x-axis. Like if you were just looking at the zeroth oscillator, you'd plug in 0 for x. If you're looking at the third oscillator, you'd plug in 3 for x. And what is x? X is not just a random x. It's x means position along the x-axis, right? So this equation is saying, oh, the position on the y-axis is fully determined for this entire arrangement is fully determined, the position on the y-axis, as long as you specify what time you're looking and how far along you're looking in the x-axis, right? Now we're almost there. So one equation can capture this whole affair. But pi over 2 was just an example. Example of what? Of the staggering step, of the size of the step, the size of the stagger, right? I just said, imagine that each one of them is pi over 2 radians out of step with its neighbor. So we did this whole thing based on pi over 2, but it didn't. But I was just asking you to imagine that pi over 2 could have been anything. It could have been pi over 4, pi over 8. But what it was an example of the step of, or example of the phase step. In general, the phase step could be any constant quantity of the phase step could have been any constant quantity of radians per meter, right? That pi over two, like what was that pi over two? It wasn't just a phase. It was how much out of phase any given oscillator was um relative to its neighbor, which ultimately meant, like, if you look at what we were just doing with the pi over two, we were saying that, like, this equation, or here, we're saying, like, by using pi over two as an example, we're saying, like, the third oscillator is three pi's over two, pi over twos ahead in phase or behind in phase from the original zero with one. So pi over two in this example represented how many radians, how many more radians were going per each meter that we look down the x-axis. Or put another way, if you look at this equation here, if you see how it works, how it could allow you to predict the y position for any given time at any given x position, you would have to plug in an x position measured in meters and multiply that by the pi over two, which would then have to be measured in radians per meter, right? It's saying for every meter, add another pi over two to your phase, right? That's what it's saying. So that pi over two thing right there before the x is measured in radians per meter, just like the omega before the t is measured in radians per second, right? So but it didn't have to, my big point right now is there's some kind of constant before the x that we need to capture this whole arrangement, but it doesn't need to be pi over two. It could be any amount of radians per meter. So from now on, that constant we will call K. Now we're going to call it K. And K, now, first of all, it's not the same K as the K of springs. I apologize. This is terrible. And there's even one more K coming in this class that's like a totally different K. So just like we had two I, and it's also not, oh my God, there's four Ks in this class. It's also not the same K as the unit vector K, and it's not any other K. And that's why I usually write it as a capital and put serifs on it. Like, you do whatever you want, but this K stands for this. It stands for the um, phase step staggering size, or size of the step in phase staggering. And it's measured in radians per meter. And I'm saying now, if you generalize, oh, and I'm saying the way to picture it is it's like, it's a constant. So it's like if you were to graph what the phase of any oscillator is doing as a function of where it is in the arrangement, right? You get a straight line. You'd get a straight line, right? Like the first oscillator's at pi over two. The next second one is at two pi over two. The third one's at three pi over two, like in our example. So the phase of an oscillator is directly proportional to where it is in the arrangement. So if you were to graph phase per in radians, if you were to graph it as a function of displacement in meters, you'd get a straight line. Well, the slope of that line, right, would be change in radians over change in meters, right? It would be change, like in phi, over change in x, like phi2 minus phi, just like slope is change in y over change in x. Only here it's not y and x, it's phi and x, right? So the slope of that line is what I from now mean as K with serifs over it, that's illegible. That's illegible. That's what I mean by K from now on. And here's the thing about K. And if you've already started lab 3, I do mean that K. This is the K in lab 3 that no one ever knows what's going on. Like whenever anybody does lab 3, they have no idea where K came. Like K's just like out of nowhere. But well, I'll get to that in a minute. But I do mean that K. This K represents the size of the step of phase staggering. But the reason I care about this whole thing, the reason we're making this whole arrangement, if you haven't already guessed, is that if you stand back and look at this arrangement and let this happen, like you let each one of these things oscillate, but you let them oscillate in phases that are staggered by a constant step, then of course, well, I shouldn't say of course, but it seems to me that when you step back and look at this thing, like all these things going up and down like this, alternating in space and in time like this, what you're going to see going across the x-axis is a wave pulse, right? You're going to see a wiggle. You're going to, like, each one is just going up and down, but you'll see visually crests and troughs moving across if you do this. I want to pause for one, like, this is how to create a wave, is what I'm saying. And it's, I mean, I'm saying this is how nature, I mean, I'm saying this is how we could create a wave in the lab. And in fact, that's what you'll do in lab 4. You'll literally create wave ripples from these phase arrangements. And or I'm saying at the same time, if you ever see a wave like in lab 3, like lab 3, you're not doing this, you're doing the reverse of this in lab 3. In lab 3, you're looking at waves and realizing at the end of the day that what waves are staggered oscillators, that what waves are a bunch of harmonic oscillations, a bunch of cosine functions in time and space. Okay, I mean, there's many different ways I could say that, but I'm ultimately saying that whenever we look at a wave in the lab or in nature, what we're really seeing is a bunch of time oscillators oscillating through space. We're seeing oscillators that were staggered in phase by a constant amount. And we're therefore seeing, well, there, well, yeah, we're therefore seeing this equation. And every time I'm writing plus, it could be plus or minus. I should really put that. Hold on, let me just fix that on them. Yeah, plus or minus. But yeah, so these are the two. I'm saying that ultimately this thing K is known as the angular, well, angular, just like omega is known as angular frequency, right? Because it's measuring radians per unit of time. This thing is known as angular wave number. Because again, just to repeat, what this thing is measuring is radians per, not time, but per space. And once you have something wiggling in time and in space, well, once you have a phenomenon, once you have a bunch of oscillators, like, and please note, you need a bunch of oscillators to do this, right? One oscillator is just that, an oscillator. One oscillator is a particle that wiggles back and forth in time in a very regular way. Once you take that wiggling, that oscillation, and you spread it out in space in a very regular way, then you have the wiggling is occurring in time and in space, and that's what constitutes a wave. So once there is space involved, so see this like, and this is again, this is like the whole purpose of lab three, but I'm not saying lab three, I mean, you're gonna look at it like from the opposite perspective in lab three. But what this is trying to say is that a wave is cosinusoidal harmonic oscillations sort of equally distributed over time and space, right? It's not just a cosine of time, it's a cosine of time and space. That's what a wave is. This is a wave. Once you have the space factor in there, it becomes a wave. And that's why K, the extent to which this is spread out in space, is called the wave number, because now it's a wave. It wasn't before. A oscillator is not a wave, but a bunch of, and by the way, a shape of a wiggle, so like something going like this, that's not a wave, that's an oscillation. In a graph, a cosine graph like that looks like this, that's not a wave either. That is a curvy shape. What a wave is this thing distributed curvily through space, or that if you draw a cosine on a piece of paper, if you draw a cosine on a piece of paper, that's not a wave. That's the graph of an oscillator. But if that cosine were to wiggle back and forth, if the crest of the cosine were to go back and forth between being a trough and a crest, if you take a cosine and you wiggle it in time, then it's a wave. Or you take a time oscillator and you distribute it in space, then it's a wave. A wave is, so I'm going to say this again. A wave is, or it consists of harmonic oscillations, harmonic, which is the same cosinusoidal, in other words, in time and space. That's the key point, which we didn't have before, but we have now. Let me go over. So I'm saying a collection of a collection of oscillators that are staggered in phase in a certain way constitutes a wave pulse. I'm going to pause for a second. Like, there's obviously a lot more to say about this. There's a lot more to say about this. But let me pause for a second. First of all, honestly, how can I raise your electronic hand? Well, first of all, just raise your electronic hand if you hear me speaking right now. Awesome. Thank you. I always love that part, or I kind of hate it, but it's like a lot of people. Okay, great. Oh, awesome. All right, so like 12 people, 12 people. Great. Thank you. Okay, you can put your hands, or 13 people. Also, you can put your hands down now. So now I'm going to ask a question. Like, honestly, it's just a qualitative question. Great. Thanks. And one or two more to put your hands down, just so I can ask this. Two more. Please put your hands down if you know how. Do you need help? Thank you. Perfect. Right. So here's my question. Honestly, so that I can go on or not go on. Do you agree with, can you see how if a bunch of things did that in this way, can you see, not perfect, like not mathematically, but can you just like see physically in your mind why I'm saying that that would be a wave? Like, can you picture the wave that I'm talking about, the wave pulse that I'm talking about, if I have a bunch of things going like this, or have I lost you with that? Does it seem like a wave to you, what I'm describing? Oh, maybe not? Oh, wait. Should I ask it? Okay. Wait. Let me ask this actively. Does it not seem like a wave to you? Like, do you actively not know what that is not a question. Um, yeah, I can, but wait, so someone just asked a really good question in the chat. Hold on. Someone just asked in the chat, can I clarify the cosine analogy? I will, sure, but a couple of things about that. I mean, it's a great question. A couple of things about that. Number one, you're going to be doing that in detail in lab three. Like lab three is all about unpacking the cosine connection, but I still will try. But number two, let me say, it's not even an analogy. It's like literally the case. that we're saying a bunch of cosines happening in time and space, and that's what you'll see in lab three. But number three, and I will try. I'm not trying to duck out of the question, but let me back up for a second before I even do that. I might not be asking my question correctly. I'm not even asking you guys yet to even see what I'm saying about cosines. Like again, like that's what you're going to unpack in lab three. I'm just saying, like physically, visually, honestly, if you pictured a bunch of springs in front of you and one was going, this is a little bit, by the way, this is a little bit like one example of this is like if you've ever been to the Brooklyn Museum in Brooklyn, like the Brooklyn Art Museum, like on Eastern Parkway, or if you've ever been there before COVID, I think this started happening again sometime recently since COVID, but I mean, that's where I used to live, whatever. It, there used to be a bunch of fountains. And there's also, I think this is also true at Lincoln Center, like not too far from John Jay, but there used to be a bunch of fountains and like one would go up and down and then the next one would go up and down and now fountains create water. I'm not, but that doesn't matter. I'm not saying that, but I'm saying that like it'd be like up down and then up down and then up down and then up down and and they would go to all different kinds of rhythms. Like sometimes these fountains would go up and then up, but sometimes they were like alternating in the way that I'm talking about here. So it'd be like, it'd be like that sometimes. And I'm just asking everybody before I go further, can you picture what I mean when I say that like crests and troughs would be traveling to the left? I mean, traveling from left to right if enough things were going up and down in an organization like that. Like, I'm just asking, can you picture why, like in English, visually, I'm saying that this starts to resemble a wave? That forget the cosines and all the math. Just like, but I'm asking you honestly, because I can't sort of go on unless we're on the same page. Do you guys, can you see how, if you, I think there's even an apparatus like this in the back of the room, in the back of the lab room, um, with like balls hanging. I don't know if it's still there, but can you picture why I'm referring to this physically as a wave? Oh, interesting. Oh, wait, things are happening in the chat. Okay, wait a second. Oh, that cosine analogy. Oh, okay. Someone in the chat, very totally multiplayer co-op, by the way. Somebody in the chat just said that they actually think the cosine analogy does help you visualize it, and they're sort of address because the other person asked, "Can I re-expand on the cosine analogy?" And I was like, "No, no, don't even worry about the cosines yet." And then another person just said, "But I think that actually helps." And I actually just realized why they're saying. I think I realized, and what the other person's actually asking for. So wait. And someone else is saying it makes sense, but I'm wondering how that's different from oscillation. Okay. And I'll go to the next page. First of all, yes, I see what you, okay. The cosine thing that I'm saying, like without getting too bogged down into mathematical details of cosines, what I'm saying to everybody is one thing going up and down, up and down. That is not a wave. Well, let me back all the way. Okay, you know what? Wait, I'm sorry. I totally will address all this. Here's the problem. I was going to do this next, but maybe I should have done this first. Let me tell you what I think a wave is, just first and foremost. So bear with me for a second. I will definitely address all these. Let me tell you, like, what I think a wave is, what I mean by a wave, even before we relate it to all this. Like, what do we mean? Like when we're standing at Coney Island or Far Rockaway and we see waves coming in like on the water, like what do we even mean by that? So hold on a second. Okay. This is so concrete, but it's so. Wait. Okay, sorry. I'm looking at direct chat and I'm looking at the time. Hold on. And you can write this down. Please do write this down. This is one of these things in physics that is like so simple, like once you think about it. But to me, it's a huge breakthrough. Like it's so simple once you think about it, but like until you think about it, like you would never think about it this way before necessarily. And just because it's simple doesn't mean it's easy. I'm going to explain in 1 second. Just hold on. There's like lots of things happening in the direct chat, just so bear with me for 1 second. Yeah. Oh, and that's good too. There's a lot of good things in the chat. Hold on a second. Okay. I'm looking. Okay. So I'm looking at the chat. There's some really intelligent things in the chat. Some of them are almost too intelligent for right now. Like I'll just like there's one keyword in the chat, disturbance. Keyword, huge, awesome word. Remind me if I forget on the next page when I define this a different way. I remind me to give a definition that uses the word disturbance. I'm totally all for that. But then there's like other things here that are almost making it harder for you than necessary. Like there's stuff about frequency, high or low frequency, or equilibrium point and amplitude. Like that's all true and like that's awesome and hold those things in mind. But right now I'm trying to even be simpler than that. And I don't mean stupider than that. I'm not trying to oversimplify anything, but I'm just trying to distill down something to its physical, intuitive essence. Here's what I'm saying right now. When you stand at Coney Island or like whatever at a beach and you see waves coming in, or or in lab three, and please just someone tell me, have you started lab three at all? Just someone tell me in the chat, have you started lab three at all? No. Okay. Sort of surprised, like, what have you been doing the whole all right, fine. Well, you will. And then hopefully this will help. Instead, lab three, each of you and your partner is going to take this long string, this long spring that's thin, and you're going to like shake one end of it, and you're going to send wave pulses back and forth to your partner and back. Okay, they're like going to do all this analysis and all this stuff and take videos, but you're going to shake a string and send pulses back and forth, and it's going to be like the one-dimensional version of when you stand at the beach and you see on the surface of the water, you see like crests and troughs sort of coming in toward you, right? And we all know at some level what it means to recognize a wave. And yes, this is all ultimately going to relate to sound and all that, but I don't and light, but I don't want I'm just talking about real life, like common sense, like what we can experience, like don't even get like, intellectual yet. Let's just like be relatable. We all kind of can recognize a wave when we see one and we call it away. Look at the waves coming in. Oh, the waves are high today, whatever. What are we talking about? When we call something a wave, what are we really saying? What we're really saying when we say, oh, the waves of the ocean are coming in and the waves are breaking, or oh, the waves are really high today. I wouldn't take that surfboard out. Well, yeah, first of all, what we're talking about is a disturbance. But yes, but like really, when you break it down, what we're saying is when we say that there's a wave coming in or a wave crest coming in, we're saying some kind of motion is occurring from there to here. Like something is moving and it's real. It's not Harry Potter, right? It's real. Well, what do we mean by real? I mean, we could literally measure it. We could be like, it's 2 miles away or 200 yards away, right? 200 meters away right now, right? And we could start a stopwatch and be like, oh, it took 10 seconds for it to go from there to here. We could literally measure it. We could do it again, or we could create it in the lab with a string. I mean, with a shaking a string, and we could talk about the motion of the thing that we're seeing in real measurement, reproducible ways, so much so that we can even make predictions, right? And you do it at the beach all the time. You like intuitively, like, oh, those things are coming in. Oh, run away now, it's coming. Like, you know that it's going to come in a certain amount of time into the same level that you know when a baseball is about to hit you in the face, because whether you're doing it precisely or not, you're literally relying on the fact that there's like an observable motion that has a velocity that can be extrapolated and predicted, just like the velocity of any particle, right? But the crazy exciting thing about a wave is that although all the physics thinking or intuitive physics thinking that we do when we observe a wave in motion, it's all true and correct. But when you stop and think about it, what you know is that thing that you're watching come in, it consists entirely of water. Right? In the case of an ocean wave, right? Like if there were no water, there'd be no wave. Or if you're in the lab and you have this long metal spring, if there was no metal, there would be no wave. Like all that you're watching is metal. If you shake a long slinky, or all that you're watching at the beach is water. But there is no individual water molecule that is going from there to here. Or in the lab, if you shake, right? Or any wave you ever think about. The thing about the wave is that there's no thing doing the thing that the wave is doing. I cannot emphasize this enough. It's really simple, but it's really huge. And I didn't think about it until I thought about it. Like the essence of wave motion is that it is not particle motion. Like particles are moving. Don't get me wrong. And motion is occurring in a totally scientific sense. But the but no individual particle is doing the motion that we are scientifically observing, right? Like, let me say it again. And I know it sounds like I'm like really upset. I'm just excited, but like it's a huge, when we're going to talk about wave motion from now on, what I mean is motion from here to there that is observable and reproducible and predictable, but for which no individual material object in the universe is going from there to there. That's what we mean by wave motion. We mean immaterial motion. Motion that is real but is not material. I'm not saying materials aren't involved. I'm saying there's no material, there's no individual object that goes from there to here when an ocean wave goes from there to here. What you're observing is a crest of water go from here to there. You're observing water, but you're observing the crest, like the bump, right? The hump, the sea, the white cap, whatever, is going from here to here. And if you really think about it, you freaking know. And everybody who doesn't do physics knows, if they think about it, that when you say, oh, the wave is coming, oh, the wave is coming, even though it's made of water, there's no water that's coming. I mean, yes, you get wet, but what's the water doing? Water over there is going down and then up, and then some water over here is going down and then up, and then some water molecules over here are going down and then up. There's no, I mean, there might be some stray accidental water molecules that might make some kind of horizontal journey, but it's not necessary at all, and it's not reliable at all, and it's not necessary for the wave to come in. What comes in is the disturbance in the water. That's a key word. I'm looking at the time, right? Like the water was flat, the water well, until there was waves. Like the water has a shape, and then there's like a contortion in the shape. There's like a bump. Or let me shift attention. When you go into the lab on Wednesday, and you're not going to do anything like you're going to take a lot of fancy measurements, and you're going to use like software and everything. But the thing you're doing is just taking a freaking piece of metal and just shaking it. You're not doing something that requires sophisticated technology. So you're just creating ripples that go back and forth on this long slinky spring. And anybody who's ever played with a slinky has seen this as a child, right? But by the way, you could do it a different way as a child. If you had a big wide slinky, you could flick one end and then you see like a right? Like you could see the little metal thing going and you could watch and you could time it and you could predict it. And all that you're watching is metal. But you all know what I'm saying. Like if you go like this and a bump in the metal travels from you to your partner, it's a bump. that traveled. It wasn't metal that traveled that way. It was some metal over here went up and then down, and then some metal over here went up and then down. And then, in other words, each individual slice oscillated, and all the slices were arranged in so beautifully, whether on purpose or by nature. I mean, whether by humans or by nature, you have these oscillation, you have these things that are going coast. Well, I'm getting back to the other question in a second, but I'm saying I know I'm like getting a lot, but I'm going to pause in a minute and I'm going to try to actually address the questions that were just asked. But I'm trying to emphasize that when I say wave motion, what I'm from A to B, I mean motion that occurs from A to B for which no individual particle, no individual thingy thing had to go from A to B. So wave motion is unthingy motion, and it's the first time we're saying that in this class, or like the first, right? It's unthingy, it's immaterial. It doesn't, I'm not saying it doesn't involve materials. I mean, that's why it's science. Like we can only create it because like there's stuff in time and space. But we're taking a bunch of little things and arranging them so delicately, or nature is arranging them so delicately. So back, okay, I will go to the chat in a second, but to go back to like all this business, this, I'm saying that if each one of these individually went up and down, what you would see this pattern. Okay, so back to the cosine thing, right? Like even right now, if I just, and this is what lab 3 is really about. Right now, I can picture like a cosine curve, right? Like if they're like in this snapshot, and if I made a lot of them and I put them even closely and spread them out, I see this cosine curve. Y is a cosine function of X. But that right there is not a wave. If it's just a snapshot, if it's literally just a cosine, that's not a wave if they're just sitting there, right? That's a picture of a wiggle. And it's not a wave, to be very specific, because each one of the crests in that cosine curve, like each one of the like this or this, is just sitting there. And if you were out in the ocean and you were like, if you were at the beach and the water, even if the water, basically what that is like a mountain range. When you go to upstate New York or something, and I'm not being sarcastic, but like if you see a bunch of hills and valleys in the terrain of upstate New York, that's interesting. That's beautiful. And you could even imagine like a one-dimensional or like a slice of it, and it'd be like up, down, up, down. Well, that's interesting, but you would never describe those mountains as being waves because the crests and the troughs are just sitting there, right? It's just heights, it's just hills and valleys. It's not really crests and troughs in any meaningful sense because the mountains aren't traveling, right? But when you go, and similarly, if you went to the ocean and you just saw a bunch of bumps in the water, like, and it was ice or something, whatever, that would be interesting, but you wouldn't call that waves. What waves are when the crests and the troughs are moving, right? So if this cosine graph started wiggling, if the trough right here, if this trough was going up and down, and this crest was going up and down, right? Which it is once we do the example. If those things are going up and down, then what's interesting is that if you stand back and look at it, one moment the trough is here, like at position 2, but then the next minute the trough is over here at position 3, or the next moment, or the next second, or whatever, right? And so if you paid attention with your eyes to troughs, you would see troughs or crests, whatever you picked. You pick some bit of the shape of that thing, and you start tracking the shape. You start tracking disturbances from the norm, the equilibrium expectation. So if you look at a bump, a disturbance, something that isn't equilibrium, you look at a trough or you look at a crest and you pay attention, then you start seeing visually, oh, that trough is moving from 2 to 3 to 4 to 5 and then back or whatever. What's moving is crests and troughs, and they're moving horizontally along the x-axis, right? This is what I mean when I say you would see a wave if if all these suckers were going up and down, you would start seeing disturbances, pulses traveling left and right. I believe that you would see that. And I believe that you believe that you would see that. And I'll ask you in a minute. Right. And the key thing is, so in other words, the key thing is that number one, if you just had one of these, that doesn't happen. If you just have one of these, it literally go. So back to somebody's question in the chat, who was like, wait, why is oscillation not a wave? Or they, well, how do they literally put it? Wait, somebody literally said, it makes sense, but I'm wondering how that's different from oscillation, right? So I'm saying oscillation on its own is particle motion. A particle can oscillate back and forth. And at any given moment, we know where it is, there it is, there it is, there it is, right? So it does exactly what the phenomenon does, oscillator. And then if you make a graph, you can make a graph of where it is in time, and the graph would be a cosine function. So that's a wiggle. But neither this nor this is a wave because, well, because of the way I'm describing it now, because nothing ever ended up moving in any direction or place that the individual particle wasn't moving. Like the graph is not moving, it's just a steady cosine graph, and the oscillator is just going up and down. But then you put a bunch of oscillators together, and if they're all oscillate, so if you spread them out in space, now the key thing is just on a visual level, and I mean this, like not calculus, not trigonometry, like people that don't care about physics at all would, I think, agree, if forced into this conversation, that like once you put a bunch of these oscillators together and they're all going up and down in a staggered way, then something visually starts moving horizontally. Even though no individual object is moving horizontally, something moves horizontally. What? And it moves in a scientific way. Like it moves at a specific rate of speed that we can then count on and make predictions about where it's going to be when. Like literally. And the thing that is moving is a disturbance, like somebody in the chat said. Like literally, it's not a thing. Like I know I'm getting all. I will shut up. I'm saying what makes that thing a wave, that which a cosine function is not. Like a cosine function is oscillation in time, and spreading out a bunch of objects into a cosine. You can make a cosine in space, or you can make a cosine in time. But either way, that's just a cosine. That's just oscillation. But you put them together, you either put one of these and spread it out in space. You either take a time oscillator and spread it out in space in a particular way, have multiple versions of it in space, or you take a space oscillation and then you wiggle it in time. Once you have both, then you have a wave, and the hallmark of the wave, what literally makes it a wave, is that there's motion that ultimately that isn't particle motion, that something in this case goes along the x-axis, and yet we cannot find one individual object that ever traveled along the x-axis. That's what I'm saying. Wait, I'm gonna write one more thing. So put more in the. I'm going to ask you. I'm going to write this with the word disturbance, but I'm going to ask you, please, in the chat, all of you, any of you, wait, in the direct chat, privately, just basically say to me, do you basically get what I'm saying? Like basically. And if not, ask me a question. But I want to hear from like a lot of. Yeah, okay, thank you, and make it private. Like I'm not shaming it. I just, if I'm going to scream and I'm going to write something while you're doing that. Okay. First only. Right. Okay. Yeah, I'm gonna look in the chat. And there's only like one more thing I have to tell you, so that's the good news. Okay, wait, I'm looking in the chat. Okay. Yes, I do. I do. Sort of. Fair enough. Sort of is fair. I think I got it. I think I'm getting it. That's fair. That's fair. Makes sense. There's a large unmasked. Yeah. There's a large unmasked movement that is not matching the range of movement of individual components. So it mimics particle oscillation. Yeah, and it's not just mimicking, it's created by particle oscillation, but it's more than right. So okay, we'll keep talking about this. But yeah, I mean, I think, and I appreciate the honesty that like maybe you don't, not everybody fully gets it yet, but I'm ultimately saying wave motion from here to there means that you have a bunch of particles that each of which you have to make a wave, you have to have a bunch of particles that are each continuing to oscillate in their own little neighborhood. You have a bunch of particles that are each oscillating in their own little region. But because they're all oscillating in a certain pattern, in a certain phase staggered pattern, then you get that the result is an immaterial movement through the particles that no individual particle is doing, but all particles are contributing to. So it's so in order to make a wave, you have to have oscillation, you have to have a bunch of oscillations in time that are alternating throughout a space. I know I've now said that like 400 times, but so another way to put it is this to use, but I think you're getting it. And look, again, in a way, this is all just a jump start on lab 3. You will have a much easier time understanding 3 from this discussion, and it'll make this discussion more clear once you do lab 3. And to be super honest, we have 4 minutes. Well, okay, I'm not going to be super honest. So another way to put it is to use the word that somebody else put in the chat, like wave motion is the motion of a recognizable or identifiable disturbance from the equilibrium orientation of a collection of particles. So you have a bunch of particles, whether they're little springs or the little pieces of metal like lab 3, or a bunch of like water molecules. You have a bunch of particles that are organized, and then what you observe is like some disturbance from their equilibrium expectation. Like you thought they would all just be in a flat line, but then you see like a bump in that line. And if you can track that bump moving through space, if you're like, right, like that's what I mean by identifiable or recognizable. Like you see a certain shape, whether it's a hill or a valley or whatever, you see it and you're like, I'm tracking that with my eye. And you watch as that shape moves through, seems to pulse through the particles. That's a wave. But it's not a particle moving through the particles, it's a shape, or it's really a contortion from shape moving through the particles. We call that a identifiable. So whether so we call that a disturbance. Um, uh, and actually, technically, ultimately, that disturbance we ultimately call a pulse. If it's a full cycle of that disturbance, we call a pulse, like a crest and a trough. And the whole collection of particles that you need for that to happen is what we call a medium. So, like, yeah, like you can't do this without a bunch of particles, but then the particles do that. So a wave is a phenomenon. It's not an individual motion. It's not an individual thing. It's an activity performed by a bunch of things. Um, Last thing to say, if whoops, sorry. Whoa, hello. If this is a wave, if this is a snapshot of a wave, you know, well, wait, 2 minutes. Hold on. For an individual oscillator, now this is another big hint for lab 3. For an individual oscillator, you know it's a cosine graph, and you know that the interval between a full cycle on an individual oscillator, full cycle is called period. Well, now what I'm saying is if you take a snapshot, and this is the last thing I'm going to say, I know it's time, or no, it's about to be time. If you take a snapshot from one oscillator to the next as they are organized in space. My original, like the original point of this whole discussion today, this, you know this, from one crest to the next in space is called the length of the wave, or in other words, the wave length, known as lambda. Period is measured in seconds. Wavelength is measured in meters. So just like omega is equal to 2 pi over t, k, the angular wave number, is 2 pi over lambda. Um, I'm saying angular wavelength, angular wave number, the new thing that we just learned about today, the step in space, angular wave number, k, is to space exactly as omega is to time. And that's time. So I will see you on Monday. Hopefully this will help you in lab. Anyway, don't try to do the homework. I'll talk more about the homework Monday. If I have to extend it, I will, but still don't try to do the homework yet, the new homework. Have a nice day.
Thank you,
Goodbye.
Professor.
Thank you. Awesome. Goodbye.